Let's talk about the serialize and deserialize binary tree. The problem description, we want to serialize and deserialize a binary tree. Notice this is not a binary search tree. That means the node value don't follow a particular rule. And serialize and deserialize is important in computer science. We want to change the JVM object into a string. That string could be easily stored on a disk or passed through the internet. On the other side of the internet, another computer can get that string and reconstruct the data structure with those string. So let's see how we can achieve this goal. In another problem, if we have a binary search tree, we can print out the pre-order traversal. Then we can use that pre-order traversal to rebuild the tree. At that problem, the rule is the first element is the root node, and next thing is we can find the boundary of the left subtree and the right subtree. The rule is the left subtree is always smaller than the root, and the right subtree elements are always bigger than the root node. By that way, we can find the dividing point. In this case, the value don't obey the binary search tree rule, so we cannot do the same way. In order to preserve the tree structure, we need to print out more elements. We need to bring more information in the serialized string in order to preserve the binary tree structure. In this case, we use a terminal node as that actual information. So pre-order traversal, root, then another root, then another root. Then we reach the leaf and we print out to null to mark this is a leaf. Then we go back at the point 9. When we visit the right subtree, that is a null, so we also explicitly print that. Again, node 4 is a root, node 7 is a root, and we print out 2 null to show this is a leaf node. And again, for 5, we'll print out those 2 terminal nodes to mark 5 as a leaf node. So with those information, later we can reconstruct the tree. The rule is like this. We know this is a root node, so the next node is also a root node, right? Then the next is also a root node. For the same arguments, the next one is also a root node, but this is a null, so we've finished the left subtree of node 1. Then what's left on the right belongs to the right subtree of node 1. And we read the next, okay, it is a null. Next one is null, so we know this node is completed with 2 null left and right tree. So when we go back, we know the left subtree of node 9 is decided. What's left on the right belongs to the right subtree of node 9. So let's read the next node, which is null. That means the right subtree of 9 is decided. And as a result, we get a complete subtree of node 9. In this case, the left subtree of node 2 is decided, and what's left on the right belongs to the right subtree of node 2. So when we analyze, when we build the right subtree, we follow the same rule. This is a root node, 4 is a root node, and 7 is also a root node. Null is also a root node. The next is also a root node, but it's null, so the left subtree of node 7 is decided. And we read the right subtree. The first element is null, then we know, oh, okay, this node is completed. That means the fourth left subtree is decided. what's remain is the right subtree with the same argument. This belongs to the right subtree of node 4, and we just exhausted the whole array, and the tree is also built. Let's take a look at the program actually. Let's run it first. As you can see, we first serialize, which is trivial in this case, and we print out the serialized string, and we deserialize. And to verify the deserialized tree is also correct, we serialize and print it again. In this case, it's correct. Let's look at the serialize. It's a pre-order traversal. The only difference is we explicitly print out now the terminal node instead of just returning. The tricky part is deserialize. We get the string, right? We get the string. First of all, we break it into array, and we convert it into a list. The reason we convert it into a list because it's easy to manage. We will see it later. Here, this is our list. In the recursive call, if the list size is below or equal 0, we return null. Otherwise, we get the first element, which is the root, and we remove it from the root. This is what's remaining in the list after we process the current node. If the current node is null, then we just return null. This is a terminal node. Otherwise, we construct a new node. And in order to construct a new node, we need to know what's the left subtree, what's the right subtree. The way to know that is first let's build the left subtree. Once the left subtree is finished, then list the elements in the left subtree is removed, and what's remaining is in the right subtree. Okay, we just explained earlier how that works. The code works exactly the same way. And one thing to notice, for a null terminal node, we only remove we only remove one element. However, if that is not a terminal node, right, the left subtree, for example, when it returns 4, 5, all those elements will be removed. You see, those elements are used to build the left tree. What's left is in the right subtree. And this is a list passed into this call. And at the end, we exhausted all the elements, and we built the tree. So this is a recursive way of building the tree with the help of the terminal node. And the cost is O(n) because we visited each node one time at the list. We visited each node one time, and the space cost is O(n) because we needed this list to store the deserialized string. Okay, another way of solving this is to use print out two sequences, in order sequence and pre-order sequence. Then use those two sequences. We could also rebuild the binary tree, as in a different problem. This solution has the same time and space complexity, so each way will work.